by Dr. Nicolas Sanchez-Gual and Jose Antonio Pons. Both are my okay. Here in Valencia. Also, the results I'm going to show today were advised for Miguel Alcubierre, who was my master advisor in Mexico. And also some results were obtained thanks to Gabriele Paloni, a PhD student as well in the University of Valencia. I titled my presentation today as Dynamical Stability and Formation of Multi-Field Broke stars. To try to understand a little bit more about why we are studying these objects, I want to introduce a quick introduction, a simple definition about what is a broke star. We understood broke stars as a stationary classical solution for self-gravitating configurations made of vector bosonic fields which have a mass and are complex. In this talk and in the references, you will find them as broca fields. And since the matter content of these objects are made of bosonic fields, they are classified as bosonic stars along its scalar cosine that is really well known, the scalar boson stars. Okay, some motivation to study these objects. For example, one can come from the cosmological point of view. These objects could be understood as dark matter candidates. For example, there is a study of 2022 from Marco Borghetto and collaborators from the United Kingdom that show that if exists an hypothetical primordial dark vector boson from the early universe, it will condensate into broke star and survive as a significant component of dark matter nowadays. Another motivation for this study comes from the astrophysical point of view. These broke stars are exotic compact objects with dynamical stability properties that could be considered as black hole mimickers, and offers an alternative in the interpretation of the strong gravity data against the black hole paradigm. For example, in 2021, Juan Carlos Bustillo and collaborators from the University of Valencia show that the gravitational wave signal 190521 could be interpreted as a merger of broke stars. And finally, the motivation to study multi-field broke stars come from the quantum physics. In this case, in 2023, Miguel Alcubierre and collaborators from the University of Mexico study using the semi-classical approximation of gravity in quantum field theory. They studied a single quantum zero spin field with a distribution of excitations, showing that this system serves space-time, the same space-time of a multi-field boson star in classical relativity. So with all of these motivations, we decided to study multi-field broke stars in this case. And for example, I want to show you here the cover of this BBC magazine, the Science Focus, where they show more or less some ideas about the broke star, the bosonic star, and they name them as dark stars. Okay, to begin with equations, I want to show you the Lagrangian density here, an action where we can quickly identify the Einstein gravity and the terms for the matter content that basically are n complex broca fields. This is basically the Lagrangian term for electromagnetism, but in this case, a massive one. We can find here the parameter mu, that is for the mass of the bosonic particles. And in this work, we are just focusing in studying spherical symmetric equilibrium configurations. Despite that, we have here a set of several fields. These fields could have different symmetries. For example, symmetry is different from the spherical symmetry. But once they couple gravitationally, what we are looking for is that couples produce a space-time that has a spherical symmetry. So we will ask to this couple the total energy momentum tensor will be consistent with the spherical symmetry. In 2016, the first answers about Broca star was presented by Brito and collaborator from the University from Portugal. They use just one field in this case. This is the answers. And in 2023, in my master program, I proposed the generalization of these answers for the case of multi-field or Broca stars. And looking for that these answers produce an space-time that is spherical symmetry. In this case, what we have is 2L plus 1 fields, where L is the angular momentum number presenting the spherical harmonic functions, and N goes from minus L to L, also presenting the spherical harmonic functions. We can see quickly some quantities here in these answers. For example, the harmonic time dependency, that is a dependency that it presents in these bosonic stars. We can see also the scalar potential here. In this case, this scalar potential is just with a radial dependency, but in this case, we put also an angular dependency given by the spherical harmonic. And the generalization in this case involves, aside the radial part of the three-vector potential, we have to include a new radial function that gives the radial dependency to the angular components of the three-vector potential. And the angular dependency for those components are given by the angular derivatives of the spherical harmonics functions. We end up that this is the appropriate way to generalize this system for a multi-field case in such a way that we produce an energy momentum tensor or stress energy tensor that is spherically symmetric. The total energy momentum tensor is spherically symmetric and also satisfy the Gauss constraint of this system. Even we tried simpler cases without this derivative, for example, but with this derivative, we showed that in that case, the Gauss constraint is satisfied. So due to the presence of the L parameter here, we call this system, this generalization, this multi-field generalization of Broca star, like L Broca stars. This is the name that we gave to these systems. So then I think it will be interesting to present some results about these new systems. For example, what I am showing here are the different radial profiles for the different variables that participate in this system. We can see first of all, these radial profiles were computed using a multi-domain collocation spectral code that I wrote in my master program as well. And we solved the Einstein equation for the Broca fields, the Hamiltonian constraint equation in isotropic coordinates. We can see here the labs and the conformal factor, and the second ADM equation for static spacetimes. These five first functions correspond to the variable fields of this system of equation, but I'm showing as well the energy density here, because I want to mention some details about that. The first of the features of these quantities is something that we were expecting. The Broca functions decay rapidly for large values of R, as we can see here. And we also have everywhere regular metric functions approaching 1 more slowly, as we expected as well. And also the energy density will give us some ideas about the morphology of the star. For example, for the case L equal to 0 or L equal to 1, we have an spherical Broca star, and if we take values of L greater than 1, we will have spherical shells shapes for the Broca stars. But maybe the most interesting property that we found in this analysis of these functions is that if we just focus in the case L equal to 1, we found that this function, A function, is constant, is different to 0 and constant at the origin. Different to 0 at the origin. Mathematically, this is not a problem. But if we try to interpret this physically, we now have a problem, because this function is in the radial component of the three-vector potential. So if this value is constant, and we also include the angular dependency here, we will have a multi-value vector function at the origin. So that will be a problem. We are basically lacking the regularity at that point. And for that reason, we rule out this solution, the L equal to 1 for the L-prop stars. So what we are doing right now in my master program, my PhD program, is use the solutions I obtained in my master, ruling out the L equal to 1 case and evolving the L equal to, the case for L equal to. Okay. These solutions, as I mentioned, are solution of the Proca equations and the constraint equations, but that is not enough to say that these systems are physical objects or astrophysical objects. To test this viability, we need to make some tests, and one of them is the dynamical stability. Another one is also the mechanism of formation, for example, but first I'm going to focus in the dynamical stability. Previous studies showed that the Proca stars for the case L equal to 0, that is the standard case, is stable under radial perturbations in one-dimension simulations. For example, Nicolás Sánchez-Gual, a researcher here in Valencia, showed that. But also Nicolás, along Carlos Herdeiro in 2023, showed that if we evolve the zero Proca star in 3D simulations without imposing any symmetry, those systems lose their spherical symmetry and migrate to other systems that has a prolate shape in the energy density. For example, we quickly can see in this plot that the line black that represents the line, the solution space for the spherical Proca stars, with these points here, will migrate to the red line that represents the prolate Proca star. What means that in this case, the Proca star with L equal to 0 and M equal to 0 will migrate to a ground state that with L equal to 1 and M equal to 0. Okay, so due to these results, we decide to go right to perform 3D evolutions, not 1D. Okay, for our numerical evolution, we basically perform the 3+1 decomposition, that is a standard procedure of the space-time. And also with the evaluation of the space-time, we have the projectors to obtain the scalar potential, the vector potential, and the electric and magnetic field for these Proca fields. In this case, we are not going to consider the magnetic field as a dynamical variable, because we could compute the magnetic field for the rotational of the three-vector potential, which is equivalent to the Gauss constraint for the magnetic field. So we are just going to evolve the remaining three fields here using the Einstein toolkit code, which is a code in 3D and an open source code in 3D with Cartesian coordinates. That is something important in this case. I'm going to show in the next slides. What we did was modify the part of the code that was already modified by Nicolás Sánchez-Gual in order to accept and evolve more than 2 Proca complex fields. And we call this Thorn, that is basically the part of the Einstein toolkit code that used to receive that name as multi-Proca Thorn. Okay, our equations for the evolution are written basically with the BSSM scheme with this metric written in this way. And these are the equations of motion for our systems for every Proca field from the set of 12 plus 1 fields. We can observe here that we have the evolution equation for the 3 remaining fields I mentioned before, but also we have an equation for this Z variable. This Z variable is defined as the error field, and basically it's defined because we need to dump some violating constraint modes that appears in this formalism. These modes has a characteristic velocity equal to 0, so they do not propagate away the grid. So to dump those modes at the violation of the Gauss constraint that they cause, we define this field using these equations to dump those modes and dump those violating constraint modes basically. This is a standard procedure that we was even performed in the case of n equal to 1, I mean in the case of a single field. In these simulations, we were using several computation resources from the cluster of University of Valencia because, for example, as we cannot evolve the case L equal to 1 because it's unavailable, we rule it out using our physical arguments. We had to begin our evolution with the case L equal to 2. And for L equal to 2, we had to evolve 80 dynamical variables. So that was expensive computationally for us. Okay, so I'm going to try to show some of the main or the first results of our evolutions. This plot I'm showing here is the solution space for our I-COOP stars for different values of L, as we can see here. We are just focusing in the case L equal to 2. And for example, if we take the solution for the maximum total mass and evolve it, we can see that this system collapsed to a black hole. Then if we took a solution that is in this branch, in the left branch, and this solution is more compact than the solution that we previously took. And this system also collapsed. We were expecting that because in bosonic stars, the solution with the maximum mass split the branch in an unstable branch and an stable branch. And the solutions in this part used to be unstable and used to disperse or collapse to a black hole. So we were expecting to obtain a solution here that do not collapse. And in fact, this solution didn't collapse, but migrate to a new configuration using its spherical symmetry, as we were expecting, because the case L equal to 0 present this scenario. So we expect that in the case L equal to 2 as a generalization, our answer is generalization. So we were expecting that for our answers also this behavior of using the spherical symmetry was also present. So now to show how the system loses the spherical symmetry, I want to show you first in this row, these three XC planes of the scalar potential of our system. For the case M equal to 0, M equal to 1, and M equal to 2. We can see them with different shapes. These all are for L equal to 2, by the way. And those Broca star fields, well, those Broca fields, when coupled gravitationally, they form this spherical system for the, for example, for the energy density, so in the XC plane. Obviously, as this is spherical in the XY plane, we also going to see it as spherical. So what happened when we evolve these systems? Now I'm showing the GIFs for this system, and they are oscillating as we are expecting from our answers. And more or less in the time 6,000, sorry, this system begin to lose the spherical symmetry.
So initially it was followed, then the standard part was empty.
Yeah.
Just a phase.
Yeah, it was a spherical show. Yes. I'm gonna show one of the final frames, for example, and we try to extrapolate these two planes. What we're gonna have, or what we are obtaining, is a toroidal structure with a shape-like form due to this distribution here in the XY plane. And that's something that worries us because this square shape form could come from the Cartesian coordinates of our system, of our numerical code. So what we want to do now is determine if this square shape structure is caused for the Cartesian grid or some physical modes that appears in the evolution. One of the tests that we performed to do that was Fourier decomposition of the axial modes of the energy density. And we evaluate this Fourier decomposition for the different modes, for the different axial modes, as we can see in this plot here, with m equal to 1, 2, 3, and 4. And what we are observing here is that the m equal to 4 modes from t equal to 0 is dominating the system and then saturate all evolution with 2 orders of magnitude greater than the other modes. So basically, we don't know if this is a problem for the Cartesian coordinates of our numerical grid, or could be a physical behavior hidden in our system. The thing is that at the end, this mode is dominating the evolution. So it's a problem for us to determine if the end state of this solution is stable or not, because maybe the stabilization comes from this n equal to 4 mode and not for physical properties. Mm-hmm. The thing is, the results show us that the system loses the spherical symmetry, but we cannot claim that the system is stable. Okay, so the second test that we are beginning now to determine if the system, if this solution is stable or not, and to try to understand if this n equal to 4 modes is physical or not, comes from the numerical errors, was try to study the formation of Broca stars from Broca clouds. A Broca cloud is here in this context a dilute Broca field, basically. We are modeling them as Gaussian profiles, and we are using a method inspired in this paper from 2015 from Miguel Silao and collaborators. They work with Schwarzschild black holes spacetime with vector hair, employing this decomposition for the space fields and for the electric and the scalar potential. And they consider also some some extra consideration. For example, they are using they are using this formalism for the initial data of the evolutions, and they are using, for example, a flat space, a conformal space with a strength incubator equal to 0. They also set the vector potential equal to 0, and the conformal part of the electric field was considered as conservative, so they introduced an auxiliary scalar potential here. With these considerations, they solve the Gauss constraint that takes this form, which is a second-order radial equation, applying just two boundary conditions where this V comes from this ansatz here, that is basically the radial profile of this capital V, that is the auxiliary scalar potential. And they are also introducing some spherical harmonic functions here. And this is the ansatz, the Gaussian ansatz for the conformal scalar potential. What we are doing now is trying to solve with our implementation of our code for the case L equal to 0 and M equal to 0, and see if with that implementation, the formation of the Broca cloud to the evolution of the Broca cloud to a Broca star is correct, and then we will try to extend to the case L equal to 2. and if we can, also L equal to 1. In this case, we are following some studies, previous studies, as I mentioned, from Miguel Silao from 2015. In this case, for L equal to 0, M equal to 0, they use this scalar, conformal scalar potential. But for the case that they used, where they were studying black holes, this potential is not a problem, because we can see here that it's singular at the origin. But due to we have a singularity for the black hole, that won't be a problem. Also, with this potential, the electric field, the radial component of the electric field, is also takes a non-zero value at the origin. That is also a problem if we look for regular spacetimes. So, well, I also have to mention that this potential was used in the study of Herdeiro that I mentioned before, 2023. For the formation of correlated protostars, but as we are looking for more physical scenarios, we going to change this potential, changing the parameter p equal to 1 to p to -1 here in this ansatz, to obtain a conformal scalar potential that behaves well at the origin and at infinity, and also produce a radial component of electric field that is 0 at the origin and behaves well at the infinite as well, going to 0. So evolving this potential with these ansatz, we first compute the initial data for the metric function, because we have to take into account that these solutions will be used as initial data for our evolution, but those were obtained solving the equations analytically. Then we have to use a code written here in Valencia using this formalism, the extending conformal flatness condition, to compute the metric functions for the initial data, and where we have all the initial data for the matter and for the metric functions, we evolve this system using our procatorn, and the problem was that we found that all of our solution collapsed or dispersed. And we found these last weeks that the reason comes from the fact that we set the three-vector potential equal to 0. The thing is that with this condition, the evolution equations are interpreting the initial data as we are evolving just a real Broca field. What we need is a complex Broca field with two independent components. So when we change this, well, we also change this condition, and we are obtaining the correct results, but I didn't put those evolutions here. I hope that in a next talk I could present them. So I don't know how much time I have. Okay, the 1 minute for the conclusions. So in summary, what we did was enlarge the solution space for the protostar. We include multi-field solutions with a richer inner multipolar structure. In these last months, we found, performing numerical relativity simulations in 3 dimensions without imposing any symmetry, that the L protostars are unstable under non-spherical perturbations coming from the numerical grid and lose their spherical morphology. And in order to find a stable ground configuration of L protostars that our solutions are showing us that is not spherical, we have begun to study of their dynamical formation using L-Procal clones. The next step for this project will be include a non-zero vector potential in all our simulations, then beginning the evolution of 1 and 2 Procal clones, and then try to reduce, if possible, the n equal to 4 mode from the simulation of 2 protostars. We will try to use spherical patches, for instance, that are available in the Einstein-Toolkit code, or maybe change the code. There is another option, a code written in UK, the GR Chombo, that is in 3D as well, but that code has available spherical coordinates for the evolution. The Einstein Toolkit just have Cartesian coordinates, and if the Cartesian coordinates are the problem in our evolutions, we be compelled to change the code at the end. So that's it. Thank you very much for your attention.
So questions, comments? I have two questions. The first one is about the motivation. Maybe I because that part. Why multi-field program? Do you expect to have several vector fields in the channel?
I guess that the motivation comes from the quantum physics side, because when, for example, there is this study about boson scalar fields, when we know that it's not natural to propose several fields coupling gravitational. So what they did was just study one field, but they quantized the field, and they with the quantization, yeah, it would appear several states. Those states that
one field in several states.
Exactly.
Positions.
Yeah, and then when they study that in the classical regime, the space-time that one field produces behaves like the space-time of a multi-field classical multi-field classical program.
How can you compute that space-time?
They use the semi-classical approximation. I don't know the details, but
I know about some works in which they try to see what happens if you superimpose space-times, in the sense that, say, you have to a mass source that is in a quantum position. So you try to figure what happens if you have like a superposition of space-time. I guess it's not exactly what they do, but these things are generally really unstable.
Okay.
And so what you're saying is that they just consider this state, this superposition. They compute some average of the certainty tensor, and they get the metric.
Yeah, that's the thing they did. I don't know if there is some a priori problems in that approach, but they basically use the classical approximation. As you mentioned, they compute the average of the the average of the states. In this case, it's just one field, quantum field with several states. They compute the energy strength tensor of those states, and they found out that the metric function behaves like the metric function of the classical multi-field probe star. Well, boson star in this case.
With the same mass.
Yeah, with the same energy and with the same angular moment. Well, yes, yeah, yes.
Okay, and then my second question. It is about the Einstein toolkit. So you mentioned that this square that appears is because you are using Cartesian coordinates, but it's not. So probably you can use a lattice that is a square, a cube, but can you consider a rectangle? Just to see if it's a perfect square, you get something like a rectangle, and you don't need to use the other code.
Yeah, that would be interesting to
try. The first step before.
Yeah, but I don't know if I can do. Yeah, I can. I think I can do it. Yeah.
So it's probably cheaper than
yes,
to other coordinates.
Yeah, to get used
to the size of each side. That's it.
Sure. Yeah. I'm going to try it. I'm going to.
So this is because you have perhaps this star within a box, right? And to make up this maybe resonant mode, the M4. Right? It's the other example. Okay, any question in the universe online? Well, okay. So, do you know, because I've asked some people in the past that they didn't give me a precise answer. So, do you know if these things can be considered as condensates, in the sense of all condensates or not?
Yeah, in the literature, they are many authors used to consider as the Einstein was Einstein condensates. But I'm not completely sure if we have enough study for do that, because I guess for that we need to introduce some quantum properties to say at the end that this is a statistic that behaves like a Bose-Einstein condensate. But they used to assume that it will form that statistic. That's why at the beginning of my talk I didn't put Bose-Einstein condensate. I put just configurations. I was talking to Miguel as well about that, and he's been at Cubierre, and he thought that maybe we need more studies in the quantum regime to say that this in fact is a Bose-Einstein condensate. Meanwhile, we are just, at least us, we are just telling us as configurations. And maybe in the future will be enough study to say that they are Bose-Einstein.
There is do you know people that are interested in this? Do you know people that are interested in understanding this?
In fact, I would like to work with those things. So, but there are people in Mexico who developed the study of this paper I mentioned at the motivations. This is here. I know that they are interested. Well, basically they did this study, including the quantum properties now for the case of a scalar field. But the classical solution for a multi-field Broca field is presently published. Basically, our solution was recently published. I guess they are going to be interested to study also in the quantum case. I would like to participate in that case, but you can go to this paper and you will find several Mexican people working in that. Again, I think one of them is Ureña. I don't remember the name, but Ureña is his last name. Yeah. And Miguel also is involved in these studies. Okay.
Okay, then, so let's thank Claudia again. Okay, so and our next speaker is Renan Batalla. Yes.
Hello.
Superposition between Brazil and Valencia. Yes. It's been
Can I share my screen?
for several months.
Can I share?
You can share the screen, yes.
Okay. Can you see it?
Yes, very well. So you can start whenever you are ready.
Okay. So thank you very much. Good afternoon, everybody. My name is Renan, and today I will talk about this work I did in collaboration with Andreu Massot, Flavio, and Gonzalo from University of Valencia, and my advisor in Brazil, Luis Crispino. The idea of this presentation is to show some phenomenology of this new kind of compact object we proposed that we call it bounded universe. Here, there is a representation of this new kind of object. It resembles a wormhole. So we have a throat connecting two different regions. So we have two different universes. The outer one is asymptotically flat, but on the other hand, the internal universe is bounded. And later I will say what we mean by bounded. Well, in particular, this one has a finite volume inside the throat. So as you can see here, we have a sort of bubble when we enter in the inner universe. You can find a first version of this paper on arXiv, but recently we have made significant progress, and I hope soon it will be there. So let me first motivate the idea of this new kind of object, call it bounded universes. As I said, it is more or less a wormhole, and a wormhole, as you know, is this interesting object with non-trivial topology, basically characterized by a throat. So we have two different universes connected by this minimal area. Usually the two universes are assumed to be asymptotically flat, but there are, of course, cases where it is not true. But basically, we have this configuration, right? Two universes connected by the throat. You know, the history of wormholes began in 1935 with Eisenhower bridge. But that solution was not a traversable wormhole. But by the 70s, people start to look for exotic kinds of matter in order to keep the throat open. And then in the 70s, they could find traversable wormholes. For example, here, one of the most famous, the Ellis-Bronikov wormhole. It resembles a Minkowski spacetime, but the spherical sector is different here. We have this parabolic behavior with a minimum when x is equal 0. X is the radial coordinate. So wormholes, as I said, are characterized by this structure, the throat, but there are other objects that we can find in the literature that also present this throat-like structure. For example, we can find these throat-like structures covered by horizons in black bounce solutions, and a more interesting case, baby universes. Okay, the idea of a baby universe is basically, imagine that you have a distribution. This distribution is in complete gravitational collapse. Then a horizon will form in the space-time. Then you have a black hole. And inside this black hole, you have the minimal sphere. And this minimal sphere, after you enter it, you are in an expanding universe. So at a fixed slice of time, you have a sort of bubble inside the black hole. Here, there is a representation of it. And recently, researchers from Valencia have found that it is indeed possible to dynamically form baby universes in Palatini FOR gravity. But as I said, there is a problem in observe the internal region of the baby universe, because the throat, or in this case, the umbilical cord, is covered by the horizon, right? So the baby universe is causally disconnected to its parent universe. Then, inspired by this, we started thinking, okay, how can we model in at least a first way to model something that is bounded inside? Then after some attempts, we could find a way to model a static version of this thing, free of horizons, of course, because we want to observe things inside the bounded universe, but from outside. So we are in the outer universe, and we want to measure things coming from inside the bounded universe. And to do it, we required basically two things. We want a wormhole, so we want something that has a throat. Then in the areal radius, the spherical sector of the spacetime, we want a throat to be present. But the internal region, we want to be bounded. So when we go to the asymptotic internal region, the spherical sector goes to a finite value. Then we used these constraints in the Ellis-Bronikov wormhole to find a model. Of course, we have several functions that we can use, and we choose this one. It is simple because outside is basically the Ellis-Bronikov wormhole, and inside we have the asymptotic boundedness condition that we were looking for. This model here has some advantages and disadvantages. Basically, the advantages are, of course, we can easily model the boundness of the internal region, because we have this capital R here, the asymptotic two-sphere radius. And we can also control how fast and how far the parabolic behavior of the areal radius changes. So this parameter here, this parameter C here, can If we increase or decrease it, we can change how far and how fast we change the Ellis-Brodnikov behavior near the fruit. However, it has disadvantages, and mainly in the numerical implementation of it, because due to this hyperbolic tangent here, we have exponential dependencies, then it is difficult to work with it numerically, and we had a lot of troubles with it. So it took a lot of time to find a way to make the integrals converge and those things. Okay, but we could bypass it, and I will show here our results. So, but first, before actually showing our results, let me discuss a little bit the structure of this model of the bounded universes. So our model can basically describe two different things. When capital R is equal to 0, we have that sort of bubble inside the wormhole. So outside, we have something that is asymptotically flat. Then we have the throat, and inside, we have the bubble, let's say. This region has a finite space-time volume. We computed it when we put it on archive. We'll see the shape of the volume as a function of the parameter C. So when we increase the parameter C, basically what we do is to diminish this bubble. So the volume diminishes as we increase the value of this parameter C. It's important to point out that in the asymptotic internal region, so when x goes to minus infinity, the curvature scalars diverge there. And we can also model other kind of object, of course, very similar, but in this case, it's no more finite. It's something that is open, but is still bounded. And in this case, the outer region is completely the same. It's asymptotically flat. It's basically the Ellis-Brodnikov wormhole. But when we enter in the inner universe, we have this structure here. So again, we have a sort of bubble, but then it goes to a two-sphere core, where the curvature scalars go to the two-sphere, right? As you can see here. So we investigated basically particles and fields living in this geometry to see what kind of phenomenology something that is bounded inside can have. So first thing we check it, regardless the value of R, of capital R, the geodesic structure is basically complete. So we don't have incomplete causal curves in this space-time, then we don't have singularities inside it. Even though when capital R is equal to 0, we have divergences in the curvature scalars in the asymptotic internal region. The point is that the only geodesic that can reach this region is radial geodesic, and it take infinite affine time to reach this region, so it's not a problem. The capital R equals 0 case is particularly interesting when we analyze particles with non-zero angular momentum. If we compute the effective potential in this case, basically this term here, we can find an approximation in the internal region, and we see that it diverges exponentially. So in the internal region, when capital R is equal to 0, we have a sort of potential barrier inside, and any geodesic that enters in the wormhole will be forced to come back to the outer universe. For example, here, we computed some geodesics entering in the bounded universe. So these solid lines here are geodesics coming from the outer universe. Then they enter in the wormhole and suffer a bounce inside and are forced to come back to the outer universe. Here you can see this behavior in the effective potential plot. Here you see the solid lines are different values of impact parameter. And when these values face the effective potential, it suffers a bounce. And regardless of the value of the impact parameter, of course, if it is different from 0, the geodesic will suffer a bounce when entering the space-time. A different behavior happens when capital R is non-zero. For example, here, when capital R is equal to 5, it's something around there. The geodesics propagate toward the asymptotic internal region and start spinning in this radius equal to the size of the two-sphere core. Recently, we investigated the stabilities of possible circular orbits in these bounded universes. So basically, we computed where are the circular orbits in this case. Here are the conditions to circular orbits exist. And basically, we have found that these orbits can exist only at the critical points of the area radius function. So, for example, in a standard Ellis-Bronikov wormhole, we can only have circular orbits at the throat, where R prime is equal to 0. So here we also have this behavior at the throat to have a circular orbit, but the internal region of the bounded universe is richer, and we can find other circular orbits inside. In particular, due to the nature of our model, we have a local maximum inside the bounded universe, and at this local maximum we have a circular orbit. So we investigated if these orbits are or are not stable. And to do it, we analyzed the Lyapunov exponents for both time-like and null-like particles. And we basically found that at the throat, as we expected, we have an unstable circular orbit because the throat represents a minimum in the area radius. Inside in the belly of the space-time, we have a stable circular orbit, and in the asymptotic internal region, if capital R is different from 0, we have a marginally stable circular orbit. So the Lyapunov exponent is 0 in this case. As a consequence, in the internal region, we can have more light rings than in the standard Ellis-Bronikov wormhole. And also, we can also have stable time-like circular orbits inside, different from the Ellis-Bronikov wormhole, where it is impossible. It's impossible, for example, to have an accretion disk in the Ellis-Bronikov wormhole. But in our case, in principle, it's possible because there is this stable circular orbit inside, and we can put some matter there, and this matter will not escape. Later, I will show it here. For example, here for light, we can put, for example, some light emitted inside the bubble, and basically these light rays are trapped inside. And here this local minimum of the effective potential is the stable light ring, basically. So due to this nature, we can also have fields trapped inside, right? Because here we have some particles trapped inside, but we can also have fields. And to investigate this kind of thing, we considered a scalar wave as a prompt, and we investigated what happens when we perturb the space-time with a scalar wave. So we consider a Gaussian package impinging from some point outside the bounded universe and interacting with it. So as we are considering the Gaussian package coming from this region, more or less, it will first interact with the peak of the effective potential, and we will measure the quasi-normal modes from this part, basically. But part of it can also be transmitted to the internal region, and due to the nature of the internal region, it will be quasi-trapped inside and will generate a series of echoes in the quasi-normal mode time profile. Here is basically what happens. So this part here is related with the quasi-normal modes. It is the same as the Ellis-Brodnikov wormhole, but different from the Ellis-Brodnikov wormhole, it does not has a tail. It has a series of echoes due to the centrifugal barrier inside. So the modes are trapped in this cavity, and in some periods of time, we can outside measure these echoes here. We can compute the time interval between the echoes by effectively computing effectively width of the cavity. So doing basically it, we can find the values of this time between the successive echoes here. And we noticed that when we increase the value of the parameter C, just remembering what this parameter does, it basically diminishes that bubble because it changes how fast the parabolic behavior changes near the throat and becomes a bounded universe, right? So when we diminish the cavity, basically, the frequency of the echoes increases, as you can see here. And the role of the capital R is when capital R is 0, we have the bubble inside, so everything that enters will be forced to come back. Then we have the series of echoes. But when we start increasing the value of capital R, basically we restore the Ellis-Brodnikov behavior, right? Because we are increasing the size of the internal universe and turning it more similar to the Ellis-Brodnikov case. So here, just to conclude, our results shows that it's important to know the entire structure of wormholes when studying them, because observational features may depend remarkably on these global structures. The throat of the wormhole that usually is what people use to characterize the wormhole is just a local quantity. So to know what has inside the throat is important to distinguish what we are seeing in the observations. We want to extend this work also to more complicated scenarios, for example, with horizons. And this is something that we are doing right now. So thank you very much. Hello.
Any question online? I don't know if there's anyone. No questions in the chat as well. No. I have questions, but we can discuss them.
Yeah. Okay, so I can hear you. Are you saying something?
Can you tell us something about the relation between the size of the bubble and the periodicity of the?
Yes. I didn't show it here, but this the size of the cavity depends on the parameter C. It's not a complicated relation. It's more or less this dependence here. We have we can find the cavity width by solving this effective potential equal to something, and doing it basically we find the time a light took to do a round trip inside the cavity. So imagine that we have someone at the throat. This person emits a photon. This photon will enter in the space-time in the internal region. The photon will suffer a bounce inside, and then someone at the throat will again measure it. So we are basically measuring this time of the round trip inside. And basically this works because the scalar wave basically is can be modeled by a wave that propagates at speed of light, right? So it works very well in our computations. And with it, we can, depending on the frequency of the echoes, we can extract the value of C. And with this value, we can determine the size of the internal region. So observations of scalar wave echoes or other signals, for example, electromagnetic or gravitational wave signals, could be used to say the size of the internal universe, if we are, of course, observing something like it.
Okay, thank you. Any other question? Yes, Amaro?
Do you have any current or future observational probes in mind to look for this technique?
Sure. I don't think with recent spectroscopy experiments we can measure something like it. It's important to point out that here we use it as scalar wave. In order to observe, we actually would have to use gravitational waves. So, but since it's a model, we don't have actually the field equations that generate it. Here we have just the general phenomenology we could expect to see. So I don't know if future advances it will be possible to distinguish, because until now we haven't seen at least one wormhole, right? So, but people say, okay, using future spectroscopy experiments, we will be able to find wormholes due to the measure of echoes and those things. But they use gravitational wave echoes as in their arguments. And since here we didn't use gravitational wave perturbations, I don't know exactly the size of these echoes. Then I don't know if if it could be measured in current gravitational or in future gravitational wave spectroscopy experiments.
Okay, thank you. So let's thank Renan again. Okay, and now we have a short break, very short break, so like 10 minutes for our next speaker. No? So we can do whatever you want. Sí, sí. Sí, sí, no, ahora sí hay que aprovechar.
Pero no estoy seguro de nada, estoy para que sea ese que los trabajo que código de
Ah, se puede hacer el problema.
la sí, sí, entonces eso pues en base a lo y podría ser para
Ya te voy a decir una cosa.
ya la
La impresora que está a través de la fuente de agua.
Oh, it's you find the well-defined classification here?
No, I'm working.
Okay. Okay.
Hopefully next year I will finish it. And I think
But why do you say?
لا عندي راس لا عندي راس ليه؟ If I will is not bad, it will be open. I can take my try to struggle.
You have Dropbox. We use Dropbox.
Dropbox no. No. You can send me Dropbox.
Email no. To me.
What?
I cannot send it by email. 300 something megabytes.
How much?
300 plus.
Oh.
Because of the emails and stuff.
So you can.
This is what I did to Alpha. I just showed him the link.
Oh.
I just send it the link to him. Then
So
he
you
downloaded
can do this. Let's see. You can use this. Because if I believe with something can be removed,
basically it's just working in junction function. So
it's not.
yes. It is working in junction condition with the correct solution. Give her f of r or f of gradients of part of it.
But you wouldn't be able to use this. So you are working with junction.
yes.
Maybe you should give us a presentation sometime next week. So we can see.
Also, I will give a presentation in my
When is it?
maybe in September.
Wow. Okay, so if we have some model, given that and we try to meet junction condition through extensive page. Can you do it?
I'm just searching and reading to get my next topic with in the PSY VHC, my topic of the thesis is huge contribution. But my previous work was on the warm inflation.
Master's.
Yes, my doctoral engineering.
Of course,
I have seen that.
I know her. You don't me, but I know him. I was the editor of some of these publications in International Journal of Geography. So,
Okay, Jose, are you ready?
Yes. Hello.
Are you
Hello.
ready?
Yes, I'm ready. Can you hear me?
Yes, perfectly. Okay.
Okay.
So our next speaker is Jose Perdiguero, who is a student from this university, but is right now in Chile. And if you can share your screen.
Okay.
So he's going to speak about.
Let me know if you can.
Yes, we can see.
Okay. How can I zoom? Maybe. Oh no. That's. Okay. Okay. Wait. Stop and let me share again. And I think now it is full screen now.
Yes, much better. So he's going to speak about gravity and applications of technology.
Okay, so I'll start. Okay, thank you so much for the opportunity to share with you what I've been working on my first year as a PhD student. And the aim of this talk is to give you a brief overview on what is this polynomial affine gravity model and how we can couple a scalar field without the use of a metric tensor in this type of affine gravity. Okay, so that's the key point of this presentation. And well, this is the basic structure of the presentation. So let's start from the beginning. So what is polynomial affine gravity? It is an alternative gravitational model where the fundamental field, it is the affine connection instead of the metric tensor. And therefore, the gravitational interactions are mediated by the affine connection, okay? And also, we want to build an action only using the fundamental fields coming from the affine connection, okay? And in its formulation, we want to exclude completely what is the use of the metric tensor. So in that sense, this is a purely affine model of gravity, okay? And I do want to emphasize that this is a purely affine model of gravity because we do not want to use the metric tensor at all when we build the model, okay? So no metric tensor here. This is purely affine. Okay, so how can we build the model? Well, to build the model, we need some fundamental building blocks. And how we can get those? What we do is that we take the affine connection and we decompose into a symmetric and antisymmetric part. The symmetric part allow us to define the covariant derivative, whereas the antisymmetric part defines the torsion tensor. Okay, and the torsion tensor, we decompose again into the A and B field. The B field, it is the traceless part of the torsion, whereas the A field, it is the trace of the torsion, it is the vectorial part. Okay? And also, it is a good practice to preserve the invariance under diffeomorphisms, which is why the symmetric part of the affine connection goes to the action indirectly through the covariant derivative. Okay? And finally, we need some sort of volume to define the action. And because we do not want to use the metric tensor, what we do is that we use the wedge product. And the wedge product does not require the existence of a metric tensor. So in this model, the fundamental fields are the A and B field coming from the antisymmetric part of the affine connection, the covariant derivative coming from the symmetric part of the connection, and the volume form defined by the wedge product. Okay. And now that we have the building blocks, how can we build the action? And to build the action, what we do is that we use a sort of the dimensional analysis technique. And to do that, we define two operators, the N and the W operator. The N operator counts the number of free index of any object, and the W operator counts the weight of the object. Okay, so the N counts the number of free index, and for every upper index, it is a +1, and for every lower index, it is a -1. So when we apply the N operator to the volume form, because we are working on 4 dimensions, we get a +4. Okay, and the only object that has a weight here, it is the volume form, which has a weight of 1. Okay. So now, how can we build it? How can we develop a systematic way to build the action? What we do is that we take an arbitrary term, which will necessarily be defined in terms of power law of the fundamental fields. Okay, and what I mean by that is that a generic term will have necessarily m times the A field, m times the B field, P times the covariant derivative, and Q times the volume form. And what we do is that we apply the N and the W operator to this generic term. Okay, and once we do that, we get this result. We get this and this one. And now comes the key part. Because we want to build an action, the number of free index the action must have must be equal to 0, because we want to build scalar densities. So when we apply the N operator to the generic term, this must be equal to 0, meaning that we cannot have any free index. And because we want to work in 4 dimensions, the volume form can only appear once, so Q must be equal to 1. Okay, so Q must be equal to 1, and we can replace this in this equation, and then we can actually find something that we call a geometrical constraint. Okay, so this is a geometrical constraint where m plus n plus p must be equal to 4. Okay, and what it means is that all positive integer solutions to this equation are all the possible terms that can go to the action. Okay, so this is a geometrical constraint that we need to satisfy in order to build the action. In this model, we do not have the freedom to add what we want to the action. We need to always satisfy this type of constraint. And what happens is that we have 15 different types of solution. Okay, but that doesn't mean that we have 15 different types of terms. I mean, what I mean by that is that for each type of solution, we can have several types of permutation, because we need to take into account different contractions, and also we need to take into account the symmetries of the object. Okay, so we need to do a very careful analysis on each type of term, and for each term, different permutations. And this actually takes a while, but once we do that, we get the final form, and I'll present to you the action, and it is this one. Okay, so this is the action of the polynomial affine gravity in 4 dimensions. And well, it has a lot of terms because of the constraint equation that we need to satisfy. But there are some nice features about it. Okay, so first of all, it is invariant under diffeomorphisms, just like construction. Sorry?
Can I ask you something? So the way you
Yes.
define the volume form, it looks to me like it's very coordinate independent.
Is coordinate independent?
No, dependent, because you just basically take the wedge products of your coordinates, right?
Yes, we are using the wedge product. Yes.
And that would be coordinate independent the way you define it. If you, for example, are using radial coordinates or Cartesian coordinates locally, that would give you a very different volume depending on where you are.
Okay. Yeah, I think there is some this dB time elevated to the alpha, beta, gamma, and delta also has a multiplicated factor that I didn't add here, but we can talk about this at the end of the. But it's something that we have taken into account. Okay.
Okay, we can discuss it.
Okay. So, where was I? Okay. Because of the absence of a metric tensor, we have this constraint equation. And because we have this constraint, a geometrical constraint equation, the number of terms that can go to the action, it is a finite one. Okay. And we call this property the rigidity of the model. Okay. So this is something that is not typically found in other modified theories of gravity, but it's something that happens here, and that is because of the absence of the metric tensor. Okay. Another nice feature about it is that all coupling constants are dimensionless, which suggests some sort, we are speculating this, of conformal invariance, and also it is power content renormalizable, which is a necessary condition, but not a sufficient condition to ensure that the model it is renormalizable. Okay, and also, even though we start with a purely affine model, we only endow the manifold with an affine structure, we can still have effective metric tensors in the space of solutions. Okay, and also in the torsion free limit, we found a generalization of Einstein's vacuum's field equations. So in some sense, Einstein's vacuum solutions are a subspace of solutions of polynomial affine gravity. Okay, and also we can couple a scalar field to the model without the use of a metric tensor, which is something that I'll show you later. Okay, so we have the model, and now what we need to do is to find the field equations of the model. And to find the field equations, well, we vary the action with respect to the fundamental fields. And the first variation is the variation with respect to the symmetric part of the affine connection. And this is the set of field equations. And what you do here is that you have the coupling constant times the term plus the second coupling constant times the second term, and so on, so forth. And you add them all together, and those must be equal to 0. And this is the first set of field equations. Then you have to vary again the action with respect to the B field. And of course, the field equations are even more complicated. And this is something that took us a while to do because we did it by hand. And then we use Cadabra to perform the computation. So this is the set of field equations for the B field. And this is the set of equation for the A field. Okay, so we have the affine model of gravity, we have the field equations, and what we want to do now is that we want to do cosmology. Okay, so how can we do cosmology? Well, we need to build an answer for the affine connection that is compatible with the symmetries of the cosmological principle. Okay, which are isotropy and homogeneity. And what we do is that we compute the Lie derivative of the affine connection along the Killing vectors to generate the symmetries of isotropy and homogeneity, which are rotation and translations. And as you can see here, there is a last term that appears because the affine connection does not transform as a tensor. Okay. So what we do is that we take the affine connection, compute the Lie derivative along those Killing vectors, and what we found is that the symmetric part of the affine connection depends on 3 time-dependent functions. Okay, but we can actually vanish the first coefficients under a time parameterization. So in reality, the symmetric part of the connection only depends on 2 time-dependent functions. Okay, and then we repeat the same idea for the B field. We computed its Lie derivative along those Killing vectors, and we found that the B field only depends on 1 time-dependent function. And then again, for the A field, we compute the Lie derivative, and we found that it only depends on 1 time-dependent function. So the final form of the accent of the affine ansatz is that the symmetric part of the connection depends on 2 time-dependent function, and then the symmetric part depends on 2 time-dependent functions. Okay, so we have the action, we have the field equations, and now we have the ansatz. And what we do now is that we take the ansatz and we plug it into the field equations. And once we do that, we get the set of field equations that are this one. These are 5 differential equations, highly nonlinear second order differential equations that we need to solve. To our surprise, we can actually find an analytical solution to this set of field equations without any assumption at all. And of course, I'm not going to the details on how you can do that, but the basic idea is that the first equation has a structure like something times C, and the second equation tells us another something times D. Okay, so that tells us right away that we have 4 different branches, and we can solve each branch. The most important branch, which has the most information, actually has an analytical solution, and the solution is this one. And as you can see here, C and eta are related to the torsion tensor, and H and G are related to the symmetric part to the affine connection. And basically, the solution is something like a power law solution. Okay, so it is a power law solution in the time coordinate. And alpha, beta, and gamma are just a combination of the coupling constant. Okay, so we have the model, we have the field equations, we have the solution to the field equation. How we can get some physics from this? The idea we have so far is that we can build effective metrics in the space of solutions. Okay, that's the idea we have so far. And how can we get the effective metrics? Well, we postulate 2 types of metrics. The first one coming from the contraction of the Riemann tensor, which is the Ricci tensor. And the Ricci tensor comes from the symmetric part of the affine connection. And the second metric tensor comes from the product of 2 torsion tensors, which is the antisymmetric part of the affine connection. And this is known as the Poplavsky metric tensor. So basically, we postulate that we have these 2 effective metrics, and in the space of solutions, we will know if we can actually interpret those metrics as an effective metric. And one of the conditions we need to make sure to use them as a metric tensor is that they must not be degenerate, meaning that we must be able to invert this metric tensor. So what we do is that we take the solution and we plug the solution into the Ricci tensor, into the Poplavsky tensor. And what we found is that the Poplavsky tensor, it is a degenerate object, so it cannot be interpreted as a metric tensor, whereas the Ricci tensor works just fine. So once we have the Ricci tensor, which can be interpreted as an effective metric tensor, that leads us to a scale factor. And the scale factor coming from the Ricci tensor describe the de Sitter and anti-de Sitter type of space solution. We also know that the cosmological constant appears as an integration constant, and we found a solution that it is something like a combination of de Sitter and anti-de Sitter solution, but in the limit, asymptotically, tends to be a de Sitter type of solution. Okay, so this is a purely affine model in vacuum. Okay, we haven't add any type of matter or scalar field to this model. So the next part is to couple a scalar field to the model. Okay, and how can we do that? Well, we can do that by using the same dimensional analysis technique. And instead of building scalar densities, what we do is that we build inverse tensor densities with two upper index, meaning that instead of applying n to the generic term must be equal to 0, or now n must be equal to 2. And now we have this new type of geometrical constraint equation that we need to solve, and all positive integer solutions to this equation are all the possible terms that we can couple the partial derivative of the scalar field. Okay, so this is a table that contains all possible terms to couple the partial derivatives. And well, of course, now we need to do the same analysis again, and for each type of solution, for each type of term, we have different types of permutation. And this is a little more simple than building the action, but still we need to do this carefully because we need to make sure that the two free upper index must be symmetric. And once we do that, we actually find the most generic term, which is written in 12, and the potential energy term rescale the volume form. And this is something that is done. Well, I don't know if this is the standard practice in the fine geometry, but we take an inspiration in the work of Hensa, where he proposed this idea. So the final form of the scalar field action is written in 13, and as you can see here, the partial derivative are coupled to the volume form, to the B and A field, and that's how we can couple the scalar field to a purely affine model of gravity without the use of a metric tensor. And something that's interesting, at least for us, is that the number of ways we can couple this, it is a finite way. It has a finite number of terms. So we cannot couple the partial derivative to whatever we want. The rigidity of the model is inherited to the scalar field action. Okay, so I think that's something like really cool, at least for us. Okay, so we have the action of the polynomial affine gravity, and we have the action of the scalar field. And now we need to vary the action again and find the new set of field equations. These are the field equations for the gamma field. They are severely modified because of the presence of the potential and the scalar field. And the field equations for the A field remain the same. For the B field are also extremely modified. And also we need to vary the action with respect to the scalar field. And equation 19 will be something like an affine Klein-Gordon equation. Okay. So these are the set of field equations, and what I want to show you is We haven't found any solutions so far, but this is the current plan we're following right now, is that first we build a model, then we find the cosmological answer, the field equations, and we solve the field equation in the framework of cosmology. Now, we couple a scalar field, we found the new set of cosmological equations, and what we are doing now is looking for analytical solutions for different types of potential. And once we found the solutions, we can build effective metrics in the space of solution and see what type of universe is described in defined geometry. And once we do that, the next chapter will be to study defined perturbation theory, which hopefully lead us to the cosmological observables. And if anyone wants to join me on this novel quest to find analytical solutions to the set of field equations, please feel free to write me or send me some help. Okay, and that's it. Thank you so much for your time.
Thank you, Jose. So any questions? Maybe Akea wants to comment something about the volume invariance.
Oh, nothing more than what I said, but
So I think that maybe there is the square root of the determinant of something, like the determinant of the symmetric part of the bits, that would make the volume invariant.
Yeah, I think
that makes it coordinate independent.
Yes, because in this form it is really dependent.
Yes. So this is in this form. Basically, you have a four-form component, which equals of tensor density is 1. But the value of a tensor density is coordinate independent. So if you change the coordinates, that one will have another value.
Yeah.
But if you don't add it, then if you don't take into account that there is a tensor density there, that might be one in some coordinates, maybe the one you're using, but not in general.
But then you are restricting that action to a specific family of coordinates.
Exactly. That's exactly what is happening.
It's like a unimodular or something like that.
Yes. So yes.
Okay. Okay. So I think we need to think about this. Okay.
I do want to apologize, but I didn't understand anything because
okay.
of the question.
Was a useful discussion. Basically, that the volume element that you are using in that action is really invariant under changes of coordinates, because if you change the coordinates, you get the determinant of the change of coordinates.
Yeah.
So you need an invariant volume. So
yeah,
actually, determinant of whatever. Using a tensor length.
So you put out the square root of the determinant of the Ricci to make the volume element invariant under coordinate changes.
Yes. Well, if we use the determinant of the Ricci tensor, in order to do that, the Ricci tensor must be well defined, and in some sense, the Ricci tensor can be interpreted as a metric tensor. And that is something that we do not want to use, but also the volume defined by the wedge product, it is also multiplied by an arbitrary function that I didn't write in the presentation.
Okay.
So this arbitrary the scalar density, the tensor density that you need, but if that function transforms in a particular way, and therefore makes it.
It is not really a scalar function. It is a density, right?
Yes.
Okay. Yeah. Well, I think it's something that we need to about the model that I don't know at the moment. And
so in the end, I think that you will need to assume, apart from the connection, the existence of a volume element that is given, like people doing unimodular gravity. They assume the existence of an external volume element, and then they fix it with constraints, for example. There are several ways in which they do.
Yeah.
You have to assume the existence of it, because otherwise you can't integrate.
Okay. Okay, yeah.
Okay, any other question or comment in the audience here or there?
I have a question.
Mare?
Okay.
Yes.
Oh, okay, Renan, please go ahead.
Okay. There is something that intrigues me in these purely affine frameworks. Do you have to modify the equivalence principle in some way? Because, of course, you have a connection. Then you have the autoparallel curves of the connection, and it describes the free-falling observers and those things. But, I mean, you don't have a metric. So, in principle, you don't have a metric in principle, then I don't know exactly how is the Einstein equivalence principle in this way, in this framework.
Yeah, well, it isn't obvious to us that there is a equivalent principle at the moment, but I think in previous work there is a proof on how you can recover that result, but it's something that I haven't done by myself at the moment, so I couldn't answer that right now.
Okay, thank you.
Okay, so Amare, maybe you want.
The dynamical and the dimensional analysis, was there any particular reason why you chose the integral values of your MN, PQ exponents? Would it not be say that the product of those quantities would give you a defined dimension, but individual exponents would be fractional? Is that not a possibility?
So why are you considering integer indices for the dimensional analysis? Is it possible to have fractional numbers?
Okay,
Yes.
so yeah, I'm sorry, if we consider.
Yeah, the numbers that you have in that table are all integer. So
Yes.
have fractional numbers?
No. I don't think you can use fractional numbers. No. I think this works only for integers numbers. I don't know. I have never heard of taking the square root of a tensor. I don't know if that's where your question is.
That's more or less like that, yeah.
Yeah, no, I'm not so sure if we can take fractional numbers, because in that case, if we could potentially take fractional numbers, then the action has an infinite number of terms.
Exactly my point, yeah.
Yeah. Well, I think it's something that I will talk to with the group about it. Yeah.
The problem there is that you would like because these numbers are related to the indices of the tensor somehow, right? So this is like, I don't know if you know the paper of T going to 4x and Altman thing, but they were kind of doing a similar thing. They were saying that they were doing it with the dimensions. The problem is that the components of tensors are not well defined.
Okay. Well,
the dimension, as far as I know. I don't know if there is a formulation for manifolds with arbitrary real dimensioning, which you can define a tangent space and you can define the dimension of it. But the end.
Okay. Well, this is very similar to what does in the first order formalism, when you use the field bank and what else? And the field bank and the spin connection to build every possible contraction by and also setting the torsion equal to 0. It is something kind of like that.
Yeah. Thanks.
Okay, then let's thank Jose again.
Okay, thank you.
Next speaker is Diane Casado. Diane, are you around? Yes. There.
Yes.
Okay, welcome. Feel free to share your screen.
Yes, 1 second. Okay. Maybe it's here. So can you see the screen?
Yes.
And hear me? Okay, nice. Maybe how should I put this in full screen? Well, maybe if it's fine this way.
Well, fine. We have a big screen.
Okay, nice.
Okay.
Let me check
So-
1 second.
Okay, so you want to try, there is any button around the right panel. And yes, Claudia, the
I can't hear you actually, or
no?
okay.
Can you hear me?
Oh, I can't hear you very well actually.
You can start.
Okay, thank you. Now I can hear you. Okay, so thank you so much, Gonzalo. Also, thanks to all the organizers for allowing me to present this talk today here in this conference. And my name is Adrián Casado Turrión. I am a postdoc at Complutense University in Madrid. And today I'm going to talk about junction conditions in modified gravity theories. Why do we need them? And their relevance for the physics of compact objects in these theories. This presentation is based on these two works here, done in collaboration with Álvaro de la Cruz Dombriz, Antonio Lobado, my supervisors, and also Alejandro Jiménez Cano and Francisco José Maldonado Torralba from the University of Tartu. So without further ado, let's go with glued solutions and conditions. Why do we need to have both glued solutions and junction conditions in modified gravity theories? So, as we all know, compact objects are one of the best probes of modified gravitational dynamics. And when we have a generic compact object, what we need to do is to glue two solutions of the field equations of the theory, an interior solution and an exterior solution, across a surface which we call sigma, the matching surface. This glued solution, consisting of both the interior and the exterior, must be built consistently, and for that reason we need some conditions that make sure that this construction is possible and well defined. Furthermore, junction conditions will in turn determine which kind of compact objects are possible in a given theory of gravity, and will also play a significant role in the dynamics of these objects, because as you can imagine, these junction conditions tell us information about the evolution of the matching surface of the compact object. So how do we glue two spacetimes together? So first, what we have to do is to take our manifolds, our base manifolds, and remove the parts of them which we do not want to glue. For example, imagine that we have a star and its exterior, which could be, for example, Schwarzschild. Of course, both solutions could extend further away from the matching surface, but of course, we only want to keep the part which is inside in the case of the interior spacetime, and outside in the case of the exterior space. That's why we select the two portions that we want to glue, the matching surface at each side at which we want to perform the matching, and dispose the other regions. With this, we get the two spacetimes and the two matching surfaces. Okay, so evidently, the two matching surfaces must be the matching surface of the glued spacetime. So we need to be able to identify the matching surfaces at each side through a diffeomorphism in order to have the matching surface sigma. Once we have done this identification, we can apply our favorite brand of glue and paste both spacetimes together in order to get the complete spacetime, which is going to be the disjoint union of the interior and exterior portions and sigma, which we take to be independent or separate from M plus and M minus. Okay. Now that we have completed the geometrical construction of the gluing of the two spacetimes, we proceed to do physics, because we have more fields apart from the metric and the other geometrical structures in our manifold. We have our matter fields, for example, and so on. So when we glue together the two spacetimes with their field contents, there is a problem, which is that in principle, those fields living in that spacetime are going to become potentially discontinuous because we are gluing them directly. If the fields are discontinuous and we plug those discontinuous fields into the field equations, their derivatives appearing in the field equations are going to be undefined because the derivative of a discontinuous function is not well defined as a function. For that reason, we have to promote our tensor fields to tensor distributions, which we denote with the same letter, but with an underline, okay, which do have a well-defined distributional derivative. And this distributional derivative can always be computed using its action, which I show here, on some set of test tensors, because we have to imagine tensor distributions as operators acting on test tensors living on the manifold. Okay? So using tensor distributions, as I said, we have well-defined derivatives, and so we can now plug our tensor distributions into the field equations and see what happens. So to do that, what we have to do is to identify the basic fields of the theory, which is those with respect to which we do variations of the action. And we have to promote them to these kind of distributions where we have these heaviside distributions, theta plus and theta minus, which tell us that we have a portion of the field which lives on one side of the boundary and another portion which lives on the other side of the boundary. Then we substitute this in the equations of motion, and we are going to get, depending on the theory at hand, first derivatives of the theta functions, second derivatives of these theta distributions, and so on. Okay? These distributions can be computed using the formula here. And for example, the first derivative of the heaviside distribution is proportional to the delta distribution. The second derivative of the heaviside distribution is proportional to the delta and to the first derivative on the delta, and so on. So depending on our field equations, on the number of derivatives that appear in our field equations, we are going to start generating successive derivatives of the delta function, which are going to appear in our field equations. So in general, in any field theory that you can imagine, all terms in the distributional equations of motion are going to be of this form here, where we can identify two distinct parts. First, in blue, we have this rho, which is what we call the regular part of the field equation, which is the one which is proportional to the heaviside distribution. And that means that this is the part which is defined only on one side of the boundary. And then in red, we have the singular part, which is a collection of terms, the precise number of which will depend on our field equations and how many derivatives we have. And these terms in the singular part are proportional to the delta, derivatives of the delta, second derivatives of the delta, and so on, depending on the field equations. There is a very nice physical interpretation of these terms, which is that they describe multipolar distributions of matter, or any other source living on the matching surface sigma. For example, the term which is proportional to the delta distribution is called the monopole or the thin shell term, because it describes a thin shell living on sigma. Similarly, the term proportional to the first derivative of the delta distribution is called the dipole or the double layer, because it does describe a dipole living on sigma, and so on with the quadrupole, etc. So now that we know which kind of terms we can have in our field equations, because distributional derivatives are well defined, it might seem that we have already solved the problem, but actually we haven't, because with distributions comes a new problem which is not present with fields, which is that distributional products in general are undefined, except in some very simple cases, such as the product of Heaviside distributions, or the product of Heaviside times delta, or perhaps the product of a number of purely regular distributions and a monopolar distributions. And from now on, I will say that a distribution is regular if it has a vanishing singular part, if it only has Heaviside distributions. And I will say that a distribution is monopolar if it only has a term proportional to the delta, and possibly a term with Heaviside distribution. Okay. So apart from these defined products, some of which require some prescriptions that you can find, for example, in our article, we have to make sure that all the undefined distributional products, which are most of them, do not appear, that these products do not appear in the equations of motion. And to do so, we have to introduce the junction conditions, okay, which will remove those products before they can even appear in our equations of motion. So with all this information now in mind, this recipe here is the way in which you can compute the junction conditions in any gravity theory of your choice. So first, what you have to do is to expand the equations of motion in terms of the basic fields appearing on the action, the metric, matter fields, etc., depending on your theory. Then you have to promote the basic fields, as I told you before, to distributions and their covariant derivatives to distributional derivatives. And with this, you have to set the first set of junction conditions, which we call consistency conditions, which are going to be the conditions guaranteeing that all undefined distributional products are going to disappear from the equations of motion. For example, to remove delta times delta or delta times derivative of delta, and so on. Once the consistency conditions have been found, the distributional equations of motion are going to be perfectly well defined, and now are going to contain parts which are purely regular and parts which are single. So the interpretation of the regular parts is obvious. It's a piece of the field that lives only on one side of the boundary. But what do we do with the singular parts? So as I told you before, the singular parts have a very interesting physical interpretation as sources living on sigma. So we can move them to the right-hand side of the equations of motion and interpret them, for example, as components of the stress energy tensor or any other sources which live on sigma. Okay? This will give you some singular layer conditions stating that the singular part of the stress energy tensor is given by a long expression, etc., etc. Okay? So, of course, not all glued solutions of physical relevance exhibit these singular layers. So sometimes we want our solutions to be smoothly matched, that is, to lack these singular distributions. For that reason, there's the last set of junction conditions that one can impose, which is the set of smooth matching conditions, which are the requisites to avoid having these surface sources and having, as I said, a smooth matching. Okay? So this is the recipe. And this can be applied to any field theory of your choice. For example, if you apply this to the simplest case, which is general relativity, you're going to find the following junction conditions. First, in order to have a well-defined Riemann tensor, and therefore well-defined Einstein equations in the distributional sense, you have to have a continuous and regular metric, where remember that this delta star means the whole singular part of the distribution inside. And we are using the notation that these brackets with the plus and minuses are the discontinuity of what's inside across sigma. So if you have that discontinuity equals 0, it means that the quantity inside brackets is continuous across sigma. Okay. So now that we have the Einstein equations well defined in the distributional sense, we move all the singular parts of the equations to the right-hand side and interpret them as a singular contribution to the stress energy tensor. So in this case of general relativity, the only possible singular source allowed on sigma is a monopole, a thin shell of matter living on sigma, which is proportional to the discontinuities of the extrinsic curvature of sigma and its trace. Of course, sometimes, as I said before, one needs to have a smooth matching, and because of that, one requires the extrinsic curvature to be continuous, which makes this stress energy tensor to vanish. Okay? So this was the case of general relativity, but you can apply this to any theory of your choice. For example, in our work, what we have done is to apply this to biscalar Poincare gauge gravity, which is a very well motivated Metric-Affine theory of gravity, because it intends to describe gravity using the gauge theory formalism and put gravity on an equal footing with the remaining fundamental interactions of nature, which are all described by gauge theories. So if we want to use the Poincare group and gauge it to get a theory of gravity, we are going to see that the field strengths corresponding to translations and Lorentz invariance are respectively the torsion tensor and the curvature tensor. And this will mean that in general, we're going to have a metric-affine theory with a metric independent of the affine structure, of the affine connection. But this affine connection is going to have vanishing non-metricity. So we are only going to have torsion. Then we are going to build the action, as usual in gauge theory, by putting inside the action all possible quadratic terms constructed with the field strengths, and we're going to get this huge action with a lot of terms, which of course can give rise to instabilities, and in fact this action has instabilities, particular ghosts. Once we have performed a stability analysis and we have removed all those ghosts, we end up with this theory, which is called biscalar Poincare gauge gravity, because it propagates the graviton, a scalar and a pseudoscalar. And this theory is much simpler than the original theory, but much more complex than general relativity, because we have the standard Einstein-Hilbert term with non-metricity corrections, a term which is quadratic in the Ricci scalar, which is similar to Starobinsky f of r. We have a term quadratic in the Holst pseudoscalar, which is given by this expression here. And then we have mass terms for the irreducible parts of torsion, which are the torsion vector, the torsion axial vector, and the pure tensor part of torsion. If you go to the equations of motion, you're going to see that this pure tensor part of torsion vanishes identically. So we are going to forget about it, and we are only going to concentrate on the torsion vector and axial vector. Okay. So as you can imagine, this theory, which is much more complex than general relativity, has a set of equations of motion which is much more complex than that of general relativity. And don't be deceived by these short expressions. Here we have simplified them a lot, collecting long expressions into some mu tensor. And the thing here is that no matter how complicated your field equations are, all you have to do is to follow the recipe that I told you before. Expand equations of motion, promote the basic fields to distributions, find the conditions to remove all undefined distributional products, then interpret all singular parts as field sources, and then finally find the smooth matching conditions. So this is what we have done for this set of equations, which has as sources these spin currents and the stress energy tensor. And what we have found is the following. So first, in order to have well-defined distributional equations, we have found that the metric has to be continuous and also regular, which is the same as in general relativity. But we also need to have regular torsion vector and axial vector, which is to remove all undefined products of singular parts that are going to appear in the equations of motion. Then, to have well-defined metric equations, we have these four constraints here, which, as you can see, are all of the form parameter times discontinuity of some quantity. Okay, remember that these alpha and beta parameters go with the square of the Ricci scalar and the square of the host pseudoscalar. Okay, so what these conditions tell us is that either the parameter is 0 or this quantity has to be continuous. So depending on the precise value of the parameters of the theory and which ones are 0, we are going to get a different set of conditions. But for example, this one is very similar to that of metric f of r gravity. Okay. So with these equations, we have already made our equations well-defined in the distributional sense. So we can now have all the well-defined distributions and move them to the right-hand side in order to see which kind of singular sources on sigma we have. And we find a very rich structure for this theory, which is much more complex than general relativity. So remember that in general relativity, we had that the theory allowed for a thin shell of matter living on the matching surface. So here in this theory, in Poincaré, in biscalar Poincaré gauge gravity, we can also have spin monopoles living on sigma, which are proportional to the discontinuity of the Ricci scalar and the host pseudoscalar, respectively. We can also have a stress energy thin shell on sigma, as in general relativity, but the expression is going to be much more complicated. You can check it in our paper. And apart from this, there's another stress energy contribution to the singular stress energy tensor on sigma, which is a stress energy double layer, which is proportional to the discontinuity of the Ricci scale. And this is very interesting because what this means is that this theory allows for matter dipoles living on the matching surface. And this is something which you do not expect to find in a gravity theory, because in principle, gravity is always attractive. So there should be no gravitational dipoles. The thing is that this theory is a quadratic theory of gravity. And one very peculiar feature of quadratic gravity theories is that precisely their junction conditions allow for the presence of these dipoles. This is the case, for example, if you have only the Levitz-Vita connection and you build all quadratic invariants, then you're going to find also double layers living on the matching surface. Okay. So if you want to remove all these singular structures and have a smooth matching, which would be the case in a star, for example, then what you would have to do is to impose these extra junction conditions, most of which are not in GR and are not similar to simpler theories such as f of r gravity. So the key takeaways of these results is that first, we can compute the junction conditions of any theory we want. And second, in this particular theory, in Poincaré gauge gravity, the singular structure that is allowed on sigma is much more complicated than in GR, allowing for a greater variety of glued compact objects. However, because the smooth matching conditions are much more restrictive, we have more conditions, this is going to have a profound impact on smoothly matched objects such as stars, etc., because the number of possible configurations is going to be much lower than in general relativity. And this happens also in other theories, for example, in metric f of r gravity, as we will see now. So now we have seen that in general, we have to expect more junction conditions, more restrictive junction conditions in theories which are not GR, and that this will play a fundamental role in the dynamics of compact objects. So which kind of examples of this can we find? So for example, as I said, let's go to one of the simplest extensions of general relativity, which is metric f of r gravity. And imagine that you want to study gravitational collapse. So you would start by attempting to generalize the Oppenheimer-Snyder model of collapse and consider a spatially uniform star, which is a star with no pressure and a density which does not depend on the spatial directions. This means that the metric inside the star is a Friedmann spacetime. And then you try to glue it to an exterior spacetime. So in general relativity, the exterior is constrained to be Schwarzschild because of Virchow's theorem, but this does no longer hold in F of R gravity. And actually, if you apply the junction conditions of F of R gravity, which is what we did here in this reference, you're going to find that the exterior must actually be very highly non-trivial and very different from Schwarzschild. Because yes, of course, you are assuming that it's spherically symmetric, but unlike Schwarzschild, this exterior has to be time-dependent, have a non-constant Ricci scalar, and have these two functions A and B, which are not multiplicative inverses of one another. And precisely the contrary of these properties, staticity, vanishing Ricci scalar, and functions which are multiplicative inverses, these are the properties that characterize Schwarzschild space. So this is a very surprising, not surprising, it's a surprising result because the metric outside the star has to be very different from Schwarzschild. And Schwarzschild is a solution of the theory. This is what is surprising. However, as I said, of course, this result is not surprising if you take into account that there is no Virchow's theorem in a metric F of R gravity. And also, if you take into account that metric F of R gravity has to be understood as general relativity plus a scalar field. Of course, because of this, and this scalar field couples to matter, what we're going to have is that the star, when it's collapsing, it's actually coupled to that scalar degree of freedom. So actually the exterior must be hairy, if you want. As such, when the star collapses, it forms, in the first stage, a black hole which is hairy, which is not Schwarzschild. Now, in F of R gravity, we have these no-hair theorems, which state that the end result of any collapse process must be Schwarzschild. So this originally hairy black hole must radiate away the hair and then lead to a Schwarzschild black hole. Okay? So this is how we have to interpret these results. So as you can see, the junction conditions tell us a lot of information about various processes, dynamical processes involving compact objects in modified gravity theories. So this was the case of metric F of R. What happens, for example, if you study Palatini F of R and you consider the same situation, a collapsing uniform density dust star? Then if you go to the junction conditions in Palatini F of R gravity derived by Gonzalo and Diego, you're going to find that these kind of stars simply do not exist in Palatini F of R gravity. Because one of the conditions is that the trace of the stress energy tensor has to be continuous. And if both pressures are zero and one of the densities, the outside density is zero, then the density inside the star must be zero and we have no star at all. Okay? So you can think, well, you know, a dust star is an idealization, right? Of course, dust stars, pressureless stars, do not exist in nature. However, this result has another interpretation, which is a bit more profound, which is that, well, when you're considering a dust star, what you intend to model is a star whose pressure is not able to compensate for the gravitational pull of the star, which is making it collapse. Okay, so this is the regime in which the star has lost the battle against gravity and cannot do anything to prevent it from collapsing, right? So the fact that these dust stars do not exist in Palatini F of R gravity means that it is not possible to consider that the interior pressure of the star is negligible in Palatini F of R gravity. So in principle, you always need to have some sort of pressure into account when you study stars in Palatini F of R gravity. And this is very nice because it can make you speculate that perhaps in Palatini F of R gravity, stars are going to be a bit bigger, and also that gravitational collapse is going to be slower and more difficult than in general relativity, for example. But of course, these questions are still open and we are currently studying them. Okay. So just to sum up everything that I said in this talk, junction conditions are a very powerful formalism to study compact objects in modified gravity theories. even though it can be tedious to find the junction conditions in your favorite modified gravity theory, it is a straightforward procedure. You only need to have to follow the recipe that I gave you before. And after that, junction conditions are going to give you very valuable information about your compact objects. See, for example, that here I have discussed some very, very simple examples, and we have actually learned a lot about the dynamics of collapse, for example, in F over gravity, and so on. In particular, with the junction conditions of theories having extra fields, you're going to find almost always that spacetimes outside stars are going to be very different from those of GR. And these novel exteriors could leave some potentially observable signatures. For example, you could have a different light ring and shadow structure, and then once you have the exterior, you could apply all the machinery of the mathematical codes that will have given rise to this conference to analyze those new spacetimes. You could have different quasi-normal mode frequencies and other observables, such as tidal love numbers, which are precisely computed using junction conditions. And I recommend you this review here by Eneko Aranguren and Raúl Vera, in which they explain with piercing clarity of outlook how to compute love numbers using junction conditions. And apart from these signatures, we also have to take into account that in modified gravity theories, there are going to be new solutions that can be glued with thin shells, double layers, or other singular structures that are allowed in those theories. And this opens the possibility of having novel wormhole solutions or vacuole solutions, and in general, solutions having some spatially confined sources. Even not so compact objects such as domain walls and other configurations that you can imagine. And precisely it is this kind of configurations that we are currently studying in collaboration with Álvaro de la Cruz and Diego Sáez Chillón, but this is still work in progress, so stay tuned for updates. And that's it. Thank you so much for your attention, and of course, if you have any questions, I will be very glad to answer them. So thank you so much.
Thank you, Adrian. Any question or comment? Well, to be quick about the double layers, can you give some example of what a compact object that could be made of a double layer?
Of course. Well, I think I do not have it here, but you can see here, for example, in Poincaré, in biscalar Poincaré gauge gravity. Okay? If you are gluing two solutions with different Ricci scalars, then you're going to have a double layer in that glued solution. So, for example, typically when you glue solutions...
Do you have an explicit construction of that?
Well, actually, we are trying to work on this at the moment. We are trying to find solutions. But for example, if you have any glued solution in general relativity, okay, in general relativity, it's not necessary to have a continuous Ricci scalar. So if you export that glued solution to Poincaré gauge gravity, for example, then you're going to have automatically a double layer for that configuration. So smoothly matched configurations in general relativity have a double layer in general in Poincaré gauge gravity, for example. And the same is true in quadratic F of R gravity and so on.
Okay, no, it would be nice to explore the shadows of those objects.
Exactly. The idea now that we have, but as I said, this is work in progress, is to, instead of having, carry over, solutions carried over from GR, we are trying to build explicit new configurations having these sort of double layers and so on, and then eventually explore the shadows, etc. Yes.
Okay, thank you so much. So it's getting late, so we have another speaker waiting. So thanks again.
Thank you.
And our last speaker of the session, of the workshop, and of the year, basically, He's coming. El HDMI no. ¿Estás conectado al Darkroom? Ya está.
Voy a conectar un Zoom
Y si quieres esto para pasar las slides.
Ah, ok.
Tienes USB normal, ¿no? Sí, apaga el audio. ¿Esto se puede soltar? Vale, si no te quieres entender funcionaría bastante breve, se lo agradecerá a todo el mundo. Okay, so our next speaker is Daniel Molano. He's coming from Colombia, the University of Los Andes. He's going to speak about perturbations in some complicated theory of gravity. Since you already have a lot of energy, so now you can enjoy wood. Whenever you want.
Okay, thank you, Gonzalo, for giving me the chance to speak here. For me, this is a very important opportunity to show our results with the expert community. Here, as Gonzalo mentioned, I am doing my PhD in the University of Los Andes, and my advisor, Pedro, is in the Universidad de Alicante. It's a long story. I want to show some mathematical results, and I want to compare general relativity with modified theories of gravity in the same way that post-Einstein theory compared general relativity with Newtonian theory. And we have very particular mathematical results. And I decided to show, in this case, show our results in the chronological order that we found only for pedagogical purposes of this talk. And motivation, okay, was as the previous talkers mentioned, we have a theoretical and observational aspect to give us to think that maybe general relativity is not the complete theory. My dream is contribute to find the next gravitational model, or find the next gravitational model. The mathematical tool is the perturbation theory. As you know, in extended theories of gravity, we have very complex equation, and as we'll show in this moment. As you know, here we have the usual Einstein-Hilbert action, and we have the Einstein field equation. This equation is equivalent to second order partial differential equation. And the next extension, as you know, is f of r gravity when I have this field equation. And if you see, we have here four order. This equation are equivalent to four order differential equation. And we try to understand and compare this theory with general relativity. And after we extend our results in this general Lagrangian, when we have a contraction of Ricci tensor and Gresham scalar, if you see X is the derivative with respect to the first argument, Y with respect to the second argument, and zeta with respect to third argument. You recover f of r gravity, of course, if this is 0 and 0, and we have the term 1, 2, 3, 4 terms of f of r gravity. Okay, to try to understand, we try to find exact solutions in f of r gravity. And the three things that we must to understand is what happens if R is constant, for example, and if in f of r gravity, if R is constant, we have general relativity as a solution if R is 0, or general relativity with cosmological constant if R is different of 0. In vacuum, of course, all of this is in vacuum. And if we have another different solution, R depends of the coordinate R. And this is for example, remember here, this is eta and alpha in these usual ansatz of spherical static symmetric solution. And line element in general relativity, we have Schwarzschild, and we have remember this for this equation 5. And in f of r gravity, we have this equation. And if you see 7 is the same of 5. And it's not 0, and we don't have the inverse in the two first component. And for example, in f of r in Starowinsky gravity, we have this kind of equation, this set of equation. If you see equation 9, is very close. Of course, it's not the same, but it's very close to oscillator harmonic equation, and this is like a frequency. And look at when lambda tends to zero, we will have some problems in the solution. This is a solution.
Why do you have a problem? Because usually when you have something like this,
tends to infinity.
Yeah, if you multiply throughout by lambda, it should be fine. It should reduce to like R limit, right?
You say that lambda multiply this and this?
If you multiply throughout by lambda?
Yes, of course. But if lambda is here and you want to give some solution, that solution depends of lambda and depends of lambda when tends to infinity, like harmonic oscillator.
Okay.
Let me show you. This is a solution of Starowinsky model in the model R or plus alpha R squared. And if you see alpha is in the denominator of each one of these. This is the spatial component and temporal component. And
this is for Ricci scalar is not constant here.
It's not constant. This is the Ricci scalar. This is the expression of Ricci scalar. You see, it's not constant. And alpha, obviously, in each of the denominator. And what happens if I use perturbation theory? We want to compare general relativity with F of R theory, the solution. And in the usual mathematical formulation of general relativity, we have the background, and we have the physical space-time, or the space-time that I want to model. And we build an extended manifold. Lambda is a parameter, could be a formal parameter or could be a physical parameter. And this manifold is a foliation of manifold between background and the space-time that I want to model. For example, here we can have Friedman-Roberts-Walker, and here we can have perturbation equation, universe with the structure. Of course, the tensors here, the tensor field in this extended manifold are restricted or are constrained for Einstein equation. This represents Einstein equation in the background, and this represents Einstein equation in the space-time that I want to model. We put here a vector field transverse to each manifold, and this vector field includes a flux between the background and the space-time, and the physical space-time. And each identification of this point and this point is not unique. It's called a gauge. And we bring the tensor, the physical tensor in this space-time. We bring to background through the pullback, and the pullback admits a representation, a Taylor representation in the background. And we can compare the quantities here with the background. This is the Lie derivative, and the second Lie derivative. And we call the zero order, the terms in the background, first order, second order, and this is the definition of the perturbation theory, of the perturbation. Our propose is in the background, we have Einstein field equation, and in this space-time, we restrict our quantities in some model of gravity. This represents some set of scalar fields or vector fields or tensor fields. It's just a form to write the most general extended theory of gravity. And we want to compare the solutions here with general relativity, like a post-Newtonian theory. Okay, we bring our tensor in this tensorial fields. We bring to the background, and we write in the perturbation scheme. This is a product of this tensor. And we have the n order, for example, of two of this product. And we do the same. We do this procedure with f of r field equation. When we have this and the metric and the Ricci and the Riemann, and we have the n order of field equation. And we have this result. We have function or models f of r of this form. We don't have the Einstein equation is equal to modified equation. And when we extend or when we generalize our results, we have that the function of this form with f of 0 equals 0 and f of r analytic, we have the same. We don't have contribution of the new theory. The contrareciprocal of this theorem have two conclusions. Of course, we have solution different to general relativity, but that solution don't tend to general relativity when lambda tends to 0. Or the another possibility is that we cannot write in the perturbation scale. I think that this solution is not analytic with respect to lambda. We published this result. Let me introduce. He's Fabian. He was a PhD student of Pedro. Here is Pedro, my advisor in the university. And Leonardo is in National Observatory in the National University in Bogotá. It's a group of gravitational cosmology. It's a big group, one of the big groups in Colombia. What I'm doing now, we, of course, there is a relation, equivalence between the scalar tensor and f of r gravity. We can see a scalar tensor in some point of view that a general theory with f of r gravity like a particular case, more or less. And if we write in this scheme, we can find this Lagrangian of the scalar tensor theory. And with this Lagrangian, we have the same result. We decided to extend our results in Lagrangian of this form. And we found that this is disconnected. And it is connected with, we add this term. With this term is not 0 in the background. Remember that Ricci scalar is 0 and Ricci tensor is 0, but the Kretschmann scalar is not 0 in the background. And with this, okay, of course, if we have a linear version of this Lagrangian, if we use the Gauss-Bonnet total divergence, we can write 21 in 22 with the redefinition of constants, and we have the same results. But okay, and this is a conjecture that after a lot of discussion, we think that if the Lagrangian is 0 in the background, or the terms are 0 in the background, we will have some class or disconnected solution or not perturbative solution. And when the solution connects, of course, this function is not linear. For example, here we can have Gauss-Bonnet gravity. We have a differential equation for the first order of that. And we are working in, for example, this kind of theory. G is the Gauss-Bonnet term. And with this Gauss-Bonnet term, we have a first order solution. Look that this is G power n, and is equal to 1. This term vanish, and this term vanish, and we will have again general relativity. Gustavo and Jonathan are in Brazil and making his PhD, and Angel, that I want to convince that all this calculation is correct. And thank you.
Thank you, Daniel. So, anybody with energy to ask questions?
So can you take us back to one? I still have some energy left.
Do you want to come back to the?
No, back. The penultimate page. No, next. Are you going back? Yeah. The last but one page.
27.
It's like 27.
I think it's slide 27.
27. Okay.
This one.
Okay.
So if I understand correctly, if n is so, this model does not reduce to the Starobinsky model, does it? The quadratic Starobinsky.
No, this is Gauss-Bonnet.
Yeah.
Gauss-Bonnet.
No, I was expecting that when lambda is 1 and n is
0.
No, it doesn't.
Yes.
It gives a short shot. In a four-dimensional,
if this is one
consistency.
Yeah.
Yeah. So,
And the fact that when you said lambda equals 0, k is force.
Here, yes. Look at this.
No, not this one. I'm talking about the r plus lambda r squared.
R plus lambda.
the previous
Previous
slides.
slides.
The previous slides.
I don't think that should be considered a problem, because when lambda is 0, in that case, not this, the Starobinsky.
Oh, okay. In the Starobinsky model.
This one here.
Yes.
In my opinion, it shouldn't be considered a problem, because when lambda is 0, you should go back to the GR equations and start everything from scratch.
We hope that, but we can have a solution different that have that kind of issue.
When
lambda
maybe
is
not happen. Maybe not happen. If we work this in a model like r plus lambda r squared,
Yeah.
maybe not happen.
No, my point is that that equation from the field equation that he showed us,
from the field
it
equation,
fails when lambda equals 0.
from
That's
the field
because
equation, not from the solution.
you should go back to the field equation and not just your
If
equation.
you in the Lagrangian, it's clear that we tends to 0 and we have general relativity.
Yeah.
But in the solution, you have the field equation. The solution could be
happening is the solution, not in the field equation.
Or the solution, if it tends to general relativity, don't admit the perturbative scheme. We can write first order and second order in comparison with general relativity.
Do you mean that for the Starobinsky model, they are disconnected, there is no perturbative approach.
Yes, it's disconnected, or the solution is not
Linear in lambda.
inland. Yes. Around the lambda, people say.
I don't think so.
Intuitively, I don't agree. I haven't done the calculation.
Yeah,
Well, I've done some calculations in the quadratic model, and the basic difference is that, well, if you have r plus lambda r squared, and lambda is a small parameter, okay, then basically, when lambda is 0, you recover the relativity, and the key difference is that the Ricci scalar now satisfies a second order evolution equation. So it is dynamic. So it's no longer like in GR that it is algebraic in terms of the matter, the trace. The Ricci in general is minus 8 pi g the trace. So if there is a matter profile that is like discontinuous, then the curvature is doing exactly the same, simply multiplied by a constant. And when you have the Zariski model, since the Ricci scalar is no longer an algebraic function of the trace, but a differential equation, if the parameter lambda is very small, then it is following the matter profile, but smoothly. The transitions are smooth because it must be continuous and differentiable. Okay. So, and the smaller the parameter is, the most rapid is this transition. Okay. So, in such that in the limit lambda 0, it's just step functions. Okay. So, I have done this calculation explicitly. So, this is why I believe that in particular the quadratic model should have a subspace of solutions that recover general relativity. There may be others that are disconnected, but in that model,
maybe we have some subspace of solution that match with trace of the tensor, but that kind of solution are very it's not analytic.
Okay.
Maybe it's smooth, but not analytical.
This is a challenge. This is a challenge for us. So we'll have more discussions on this.
Yes.
Okay.
So I need only to know how you, from where you got the solution and where for the model R plus Strabonescu model. To get a non-trivial form of Ricci scalar. I wanted to know the reference of this.
Is from from Turkey.
Yes, the one. Yes, this one.
This
So
is
this
is the reference. You can make a intensity per field.
Too many parameters. Too many choices.
Yeah.
I don't know what to,
So
to decide.
this is
the value of those parameters.
this is the first time to see that for Strabonescu.
So many parameters.
You can fit anything.
So many parameters.
Anyway, this issue of the need to have an invertible f prime for that correspondence between scalar field models and f of r.
And what happened in a scalar field?
I mean, in general, in principle, it should be possible to map any f of r theory to scalar field.
We
model.
try to generalize scalar field, but it's not clear. Yes, it's the perturbation equation is difficult. It's not clear to have a conclusion in general.
Okay, so any question online? Anybody is online? Okay, I think it's time to finish and thank Daniel again. Okay, so this is the end. Thank you, especially to our guests and invited speakers for being here from the beginning to the end. We don't have any other place to go. So you are our prisoners from the beginning. So I would like to thank everybody for their contributions, line and also the audience in both sides. Well, to be able to continue this kind of meetings in the future. So thanks to all for coming, and this is the end. Thanks.
Thank you.